Swayam Prabha. Digital India. Educated India.
Towards the end of the last class, we were looking at the problem of core annular flow in a cylindrical microchannel, okay. And the idea is that this is similar to the stratified flow, where we had two liquids flowing side by side in a rectangular geometry. Here you have again two fluids flowing side by side, but one fluid is completely encapsulated by the other. Now, there is just one fundamental difference which I wanted to emphasize, and we will possibly look at it again later, okay. So, the core annular flow is similar to the stratified flow. It is also stratified flow, since here again the two fluids flow side by side. Okay, but there is a small difference which I want to emphasize, but there is a difference. Okay, let me explain to you what that difference is. So, this is the geometry. Let us say this is fluid 1, this is fluid 2. So, in the center core, fluid 1 is flowing, in the annulus, fluid 2 is flowing, okay. You can again calculate that this is the z direction and this is the radial direction. I mean, you can simplify the Navier-Stokes equations like we did last time and show that dp1 by dz is constant, dp2 by dz is constant, okay. But what we argued earlier was that P at any z, the two pressures for the rectangular channel were equal, okay. So, for a fixed z, is P1 equal to P2. That is, I locate, I fix my z position and I look at the pressure of this fluid, pressure of this fluid, and what I want to show you, ask you to do is look at the cross section. Look at the cross section. This is the core and this is the annulus, which is P2, which is solid, and this is the interface between the two liquids. Now, because this interface is curved, okay, and there is going to be a surface tension between the two fluids, there is going to be a difference in the pressure. So, what I am trying to tell you is the pressure, there is going to be a constant difference in the pressure, and that is given by this Young Laplace equation, which tells you that P1 minus P2 is gamma divided by R1. Let us say this radius of this is R1, okay, R1. In the rectangular Cartesian coordinates, we said that the pressure was equal, but now there is going to be a pressure difference, because this pressure difference arises because your interface is curved and because of the surface tension. In the rectangular Cartesian coordinates, what is the radius of curvature? It is infinity, because it is flat, and therefore it is P1 minus P2 for the rectangular coordinates. For rectangular system, R tends to infinity because interface is flat, and P1 equals P2. Okay. So, everywhere the pressures were equal in the two liquids, whereas here there is going to be a constant pressure difference between the two liquids, because that pressure difference is what keeps the surface curved, the interface curved. Okay. I am going back to rectangular geometry now. This is H and this is capital H, and this is P1 and P2. Because P1 and P2 are equal, the interface remains flat. Imagine if P1 is more than P2, okay, what will happen? If P1 is more than P2 at any point, the interface will, where the pressure is high, it will deflect upwards. P2 is low, P1 is high, so it is going to push the interface, right? And if P1 is less than P2 at a particular point, you would have the opposite situation. Okay. So, because we have assumed that the interface is flat, we were able to conclude that the pressures are equal. If the interface is going to be curved, like in the case, that means there is a difference. Okay. In the cylindrical geometry, you had a curvature, it was curved, therefore there was a pressure difference. So, pressure difference will induce a curvature, or if there is a curvature, you will have a pressure difference which is balanced by the surface tension. Okay. That is the point I am trying to make here. So, while you look at the cylindrical geometry and the rectangular geometry and you say, look, they are very similar, but there are subtle differences which you need to understand. Okay. So, let me just repeat one more time. In the circular geometry, there is a pressure difference between the two fluids at every z, every axial position. The reason why there is a difference is because of the curvature of the interface. Okay. Whereas in the rectangular geometry, if you assume that the interface is flat, the pressures are going to be equal. This is the case where the pressures are equal, but if pressure is P1 is more than P2, the interface will deflect, and then you get the curvature, and that is going to be given by, again, surface tension times the radius of curvature. Okay. So, I mean, that is the point. I want to talk about how we can get some idea about what the velocity for the rectangular geometry, what would be possible shapes for the velocity profile. Okay. I mean, we are going to calculate it, of course, but even without going through a calculation, is it possible to come up with some kind of an intuitive physical way of trying to predict what the velocity profiles are. Okay. Can we infer the velocity profiles in the rectangular geometry okay, without solving? When I say without solving will give a quantitative information, without solving means qualitatively can I get an idea, qualitatively, okay? Solving, can I get qualitative information. Now, you remember the derivation, we got the velocity for the first fluid and the second fluid, they were both varying as y squared. I mean, you integrated the equation 2 times and you got v1 of, or u1 of y is dp by dx y squared by 2, both of them were y squared by 2, okay. So, what we expect is that both the velocity fields are going to be like a parabolic, because when you have y squared, so u1 of y, recall u1 of y and u2 of y have a y square dependency. So, will both the liquids have a parabolic velocity profile? Will the velocity profile in both the liquids be parabolic? That is my question, okay. Will the velocity profiles in both the liquids be parabolic? Okay, that means, can I have a situation like this? I mean, this is 0, okay, this is also going to 0. So, is this possible? So, this is also parabolic, this is also parabolic. Now, what I have done is I have ensured that the velocity is continuous, right, because that was the condition we had, velocity is continuous, and this is 0, and this velocity is 0, this velocity is also 0, because it satisfies that. I am going to argue that this velocity is not possible. The one of the boundary conditions we have to satisfy, remember, is the continuity of shear stress, okay. The continuity of shear stress what does it imply? Mu1 du1 by dy equals mu2 du2 by dy, okay. Now, what is the derivative of u1 with respect to y in the upper fluid here? It is positive. The derivative of the u1 with respect to y in the second fluid is negative, okay. So, this the du1 by dy, the way I have drawn it, du1 by dy is positive, du2 by dy is negative, and clearly the viscosities are all positive, okay. So, you cannot have a situation where a positive quantity is equal to a negative quantity, okay. So, that means this is not possible. This boundary condition has to be satisfied, and if you have two parabolas like I have drawn it, it means at the interface one positive quantity is equal to one negative quantity, okay, because viscosities are positive. So, du1 by dy is positive, du2 by dy is negative, and not possible. This is not possible, okay. So, what this means is you will have only one maxima at best. So, we will have only one maximum in the profile. That is what it means. I can't have two maxima, okay. This is two maxima, one maxima here, one maxima here, that is not possible. And so, you could have a velocity like this. Okay, I mean this or some I'm just drawing something schematically. Okay, not a straight line. Or it could be, the maxima could be in this fluid and it could be like this. Maybe I should not draw a straight line here, I should draw something else, some curve there. So one of these two is possible. Okay, I have ruled out the fact that you can have two maxima, only one maxima. So the maxima can lie either in the second fluid or in the first fluid. What is going to decide this? The only thing which is the property which is going to decide the flow is the viscosity. Okay, so clearly if the maxima is in this fluid, that means this is the first fluid, mu1 and mu2, and this is also mu1 and mu2. Okay, here mu1 must be less than mu2 because it's less viscous, it will flow faster, and I'm going to have a maxima in the first fluid. Here mu2 must be less than mu1 and I have the maxima in the second fluid. Okay, because it's less viscous, I'm expecting it will flow faster. So basically what I'm trying to do is, I'm trying to tell you that you should be able to interpret your results on the basis of physical arguments. I mean, you can write all the equations, you can solve all these equations and you can get some results, but you have to physically understand if those results that your code, your program, your experiments are giving actually make sense or not. Okay. The other important point which I want to make here is, at this point here, the velocities are continuous, but the derivatives are not continuous. The derivatives are not continuous because du1 by dy is not equal to du2 by dy. It is mu1 multiplied by that which is continuous. Okay. So at these 2 points at the interface, the derivatives are not continuous. Okay. If mu1 is equal to mu2, then the derivative will be continuous. They are not continuous as mu1 is not equal to mu2. Okay. So these are some subtle points which I wanted to bring out, okay, so that you can understand the physical problem better. What you have done is you have been able to find something about this velocity profile for stratified flow. Okay, so and you have a particular, given a particular pressure drop and given maybe the interface position, you can find the velocity field. That is the stratified flow you have. The question is, just because you have found the velocity profile, if you were to do an experiment, okay, with those particular flow rates and you calculated what the flow rates were, right, given a particular velocity, given a particular given a dp by dx pressure gradient and an h by h, we can find Q1 and Q2, the flow rates of the two liquids. That is what you saw yesterday. And now I can find the velocity profile, I integrate it, I get the flow rate. Now if you do an experiment with those flow rates, okay, if we do an experiment with these Q1 and Q2, will we get stratified flow? Okay. The answer is you may get, you may not get. Okay. And you may get. I am going to basically briefly talk about stability for 2 minutes, because we are not going to talk about it in this course, but there is something called stability, okay, of the steady state of the velocity field. See, whenever you are doing an experiment, okay, there is always going to be some disturbances in your experimental setup. You will not be able to maintain your flow rates exactly at Q1 and Q2, okay. There will be some small deviation. However perfect your pump is, there will be some small error, okay. So, what happens is, when you have the small disturbances, the steady state is going to be perturbed, okay. The interface will get perturbed, interface won't be exactly at H. So, how does this disturbance grow in time? That is the question, okay. So, if the disturbance keeps growing, then you have an unstable state. This is exactly like what you do in process control, okay. You give a small disturbance at a steady state, and if the disturbance grows, you have instability. So, same thing here. If you give a small disturbance to the stratified flow, maybe this interface will, the disturbance will grow, and you may have instability. So, you won't be able to see stratified flow, okay. So, what you have done is you have found a solution, but you have not done anything to find out if that solution is stable or unstable. Like what you would do in process control, you calculate the eigenvalues, and then you will say it is stable or unstable, okay. The eigenvalues in the left half plane, real part is negative, you do some analysis. So, we have not done that, we have just found the steady state. So, if the steady state is stable, okay, then you will be able to experimentally observe it. If the steady state is unstable, you will not be able to observe it experimentally, okay. So, idea is, if the steady state is stable, we will observe stratified flow. If it is unstable, we will not observe stratified flow in an experiment, okay. So, what happens? What's going to happen? Okay, I mean, if you don't have stratified flow, what's likely to happen? I'll just discuss one possibility what will happen, and then you will see. Okay, so suppose for a Q1, Q2, we experimentally observe stratified flow. What does that mean? It means the stratified flow is stable, because I am able to experimentally observe it. When experiment, there will always be disturbances, and in spite of all those disturbances, I am seeing the stratified flow, okay. This implies stratified flow is stable. Now, if I decrease Q1 and Q2, okay, and I may or may not get a stratified flow, but one possibility that can happen is this interface, because of the disturbances, will get deformed. You will see some kind of a wave along the interface, okay. I have decreased the two flow rates for one particular Q1 and Q2. I am getting stratified flow. Now I decreased it. and I am trying to explain to you what I mean by instability. When I decrease the flow rate, how does the instability manifest itself? The interface will start deforming, okay, and maybe this amplitude of this interface becomes very large, okay, and this entire liquid, as the amplitude of the disturbance increases, we get, what is this thing called? Something like, I mean, this becomes very big, okay. This is, and this one fluid may get may hit the wall, and it may break, and you may get drops of one fluid in the other, okay. This is liquid 1, this is liquid 1, this is liquid 2. So you will get a different flow pattern, different flow regime, what we call either droplet flow or slug flow, okay. This is a slug flow or droplet flow, okay. And what is going to decide this? This is going to be decided by the interfacial forces, the surface tension forces, which are going to be acting on the interface. So you have surface tension forces, and if the surface tension forces are dominant, then the surface tension forces will try to break the interface and give you drops. If the surface tension forces are not dominant, the inertial forces are dominant, then you will get stratified flow, okay. So what I am saying is, this case, this is seen when the surface tension forces dominate, okay. So basically the ratio, if you have ratio of inertial to surface tension, this is the ratio which is going to decide the flow pattern, okay. If this is high, I get stratified flow. If this is low, I will get this dispersed flow, slug flow, okay. This is high implies stratified flow, low implies slug flow. That means the interfacial forces are dominant, and then it will break the interface into small drops. So this is very analogous to what we have already seen before in the context of single phase flow, where you were talking in terms of Reynolds number, okay. So what is this analogous to? This is analogous to single phase flows. For low RE, we have laminar, and high RE, you have turbulent. Okay. See, the Hagen-Poiseuille velocity profile that you have, Vz of r is dp by dz by mu 1 minus r by r whole squared. Hagen-Poiseuille velocity profile, which you found out for laminar flow, is going to be valid for all dp by dz, right. So you will say, look, I keep any dp by dz, I should get my parabolic field. But experimentally you do not see the parabolic field if the dp by dz is very large, because the velocity becomes large, your Reynolds number becomes large. So, although the Hagen-Poisson velocity field is a possible solution, you do not experimentally observe it, okay, because that is unstable. Beyond Reynolds number 2100 it becomes unstable, and it becomes what you see is turbulent flow, okay. So, there is no question of interfacial forces because there is only single phase, but there is only question of inertial and viscous forces, okay. So, here the Hagen-Poisson parabolic profile is always a solution, okay, for any dp by dx. So, if I tell you what is dp by dx, you can find what the velocity is. But when you do the experiment, if the dp by dx is very large, okay, and your Reynolds number is large, you can't get the parabolic profile. So, although solution says it's parabolic, you don't get. Same thing laminar. In the stratified flow, you found the stratified flow. What I am saying is you may not always get it because it's unstable, and that is the reason when you do two-phase experiments, sometimes you get slug flow, sometimes you get stratified flow, okay. And what decides how do you find out this transition from one flow to the other, because you have to find the point where things become unstable, okay. So, I just wanted you to be very clear about this thing. Just because you have found a solution does not mean experimentally you will get that solution, okay. So, that is the point, okay. For large dp by dx, Reynolds number is high and we do not observe laminar flow, okay, although laminar flow is a possible solution. If you remember, I told you that people have observed laminar flow for up till Reynolds number 10 power 5 in the first class. That is because they did those experiments very carefully and tried to eliminate disturbances. So, if you can actually take a lot of pain and make sure that there are absolutely no disturbances to the flow, then you can push this limit of 2100 to a larger value. But typically that is not done, the disturbances will always be there, okay. And that is the reason, we stop at 2100 and say 2100 is your transition. So, this particular example that I have taken was just to illustrate some basic ideas where you understand physics, that any problem you have to think about it both physically and mathematically, okay. You think about a problem in both ways to get a better perspective. So, now what we will do is, we will start getting into the course by way of introducing some basic concepts. The strategy is that we will derive the conservation laws for mass momentum, okay. We will do that using what is called the Reynolds transport theorem, and I will try to put things in perspective with what you already have seen in the past, so that you can get a better understanding. Now, before I do that, I want to talk a little bit about what is this thing called the continuum approach in transport phenomena in fluid mechanics. So, no, whatever we are doing, I mean most of the time we use this continuum approach. So, when we talk about things like what is the velocity, what is the temperature, okay, in a particular fluid flow, each fluid is made of molecules, right? We are not tracking the velocity of each molecule, because if you look at liquid, if you want to look at what the velocities are for each liquid molecule, that will be 10 to the power, I don't know, 40, 50 molecules. And you will, no computer will be able to, talk about taking into account the interaction of all these molecules, the velocities, and then predicting the flow. Okay. Same thing in gas. You will have a lot of molecules, and you cannot go down to the level of individual molecule and look at what is the velocity of this molecule. When I say velocity, I am not talking about velocity of the molecule. So what I am doing is, I am going to be finding what is the average velocity of a bunch of molecules, okay, and the velocity that I am talking about is the velocity of the bunch of molecules which are occupying a particular point or a particular position, okay. So this is based, and I need to choose this collection of molecules, I need to choose this size of this over which I am doing the averaging to be not too big, not too small. If it is too small, then I have only one molecule in each, volume element. I won't be able to get a good average. I need to get a good average, okay. So the volume element over which I am doing the size over which I am doing the averaging should be such that I have enough molecules so that I get a good average, and at the same time I should be able to capture spatial variations. If I take the volume element to be as big as the whole room, what will I get for the average? I will get only one value. I will not be able to find out what the variations are in space, okay. So if I take a very big size for doing the averaging, I will lose spatial information. If I use very small size for the averaging, then I may not get a good average, because I don't have enough people to average over, okay, enough molecules to average over. So I need to make sure I choose a large enough size to get a good average, and it should be small to get a good spatial distribution. Is this clear? So that is the whole point of what we are trying to do. So here it is computationally impossible to find velocity of each molecule and consider interactions of molecules. Since the number of molecules is large, okay, I think I'll put large in large. So what do? We therefore, we hence talk about velocity temperature of a collection of molecules, okay. Now this collection should be large enough to get a good average. So you might say, look, I'll take 100, a small size, and see the average, take 200, see the average. If it's not much of a difference, then it's good enough, okay. But if the difference, when you keep changing the size, that means you want to possibly take a larger size, okay. So you need to, I mean, this is just a abstract concept which you have to understand what we are doing. When I write my equations tomorrow, the Navier-Stokes equation, the velocity is that of not of an individual molecule, that is the point. Okay. Now, if the size over which we average is the size of the system, okay, if it is the size of the system, whatever the system is, okay, then the average will have only one value, that is, this is called lumped parameter, and we lose information on spatial variation. You won't be able to get, because if this is your system, you take an average of the whole thing, you will get only one velocity, one temperature, but you don't know if the temperatures vary from one point to another, which is of interest to you maybe. Okay. So, supposing you have a catalyst which is sustaining an exothermic reaction, okay, what I expect is the temperature at the center of the catalyst will be very high, and if you do the average over the entire catalyst, you will get one value, but and let us say the average is 300 Celsius, and so okay, my catalyst is performing well at an average temperature of 300, but maybe somewhere in the center of the catalyst my temperature may be 450, okay, because it is actually varying inside, because what you have done is you average the whole thing. At 450 maybe my catalyst gets deactivated, it gets sintered, or some side reaction is taking place. So, therefore, you need to have spatial information, how things vary spatially, okay. So, that is the point I am trying to make, okay. So, we hence show in a catalyst pellet, okay, sustaining an exothermic reaction, temperature is high at the center, and if we average over the whole pellet, we will not get this high temperature in our calculation. And so, if there is a possibility of a catalyst deactivation or something going wrong, you will miss it in your calculation, okay. So, we may miss the catalyst sintering or deactivation, because average temperature may be much lower, okay. If you take the full, if you take the average over the full catalyst, if we take average over the full catalyst, I have spoken about, so it could be velocity, it could be temperature, whatever it is. So, what you are doing is you are basically trying to do finding out velocity, temperature, etc. for a bunch of molecules, sufficiently large number of molecules to get a good average, and you are talking about this average. This velocity is the average velocity, the temperature is the average temperature, okay. And you do not want it to be too big. When it is too big, then you lose spatial information. If it is too small, you do not get good average, okay. So, I mean what is the good number, I do not know, but this is the concept that we are doing when we are trying to solve problems in the rest of the course. So, this is a very key point which you people should understand, that we are using this continuum mechanics approach, okay, continuum theory. Now, so just to give you a small brief of what is in store for you in the coming lectures, we are going to discuss this thing called the Eulerian approach versus the Lagrangian approach. This is one thing we are going to talk about, and then we will quickly go on to the derivation of Reynolds transport theorem, okay. Then we will derive the equation of continuity and the Navier-Stokes, okay. I mean that is the immediate future. I mean this is possibly what we are going to do in the next 2 or 3 lectures. So that once we establish all of this, then we will look at solving some different problems and looking at some applications or whatever, okay. So, this we are going to establish the theory in the next couple of lectures, and that should help you. Thank you.